In this video, we are going to work through a conservation of energy problem in physics that involves a box moving up an incline with friction. So let's jump right into this example. It says a 5 kilogram box is sliding along a horizontal surface at 22 meters per second when it encounters a frictionless inclined plane which meets the horizontal at an angle of 30 degrees. The coefficient of friction is mu equals 0.3. How far up the incline will the box slide before it stops? So I've gone ahead and sketched out this situation here. We have this 5 kilogram box and it has just encountered this inclined plane and it's moving at a velocity of 22 meters per second. Now we know that this box is going to slide up this inclined plane by a certain amount. And our question is, how far up the incline will it actually slide before it comes to a stop? So here's how we can set this problem up. We can say that the initial work W put into the system plus the potential energy of the box, we'll call that the initial potential energy, plus the initial kinetic energy must be equal to the final potential energy. So once the box is actually up here, somewhere up the incline, plus the final kinetic energy of the box, plus any energy lost due to friction. So this looks like a very long equation, but what we'll notice is that some of these variables won't even come into play. So if we consider the work being done, in this example, there's no force that's pushing or pulling this block up the incline. So it has some initial velocity, but there's no work that is actively being done to push or pull the block up the incline. So in this case, there will not be any work being done or work being put into the system. And we'll also notice that when the block encounters the inclined plane, it's at ground level, so it actually has no potential energy because it has no height associated with it. But it does have kinetic energy since we know it's moving at 22 meters per second. Now, if we move to the right side of the equation, the box is going to have some final potential energy because once the box is actually up here on the incline, it will have a certain height associated with it, so it will have potential energy. But remember we said we're interested when the box stops. So when it stops, it has no kinetic energy. So there will actually be no final kinetic energy. And we also know that there is going to be some energy lost due to friction because we're told that the coefficient of friction is 0.3. So really, this whole equation simplifies to the initial kinetic energy is equal to the final potential energy plus the energy lost due to friction. So let's go ahead and fill in the formulas that we know. So for the kinetic energy, that's equal to 1/2 times the mass of the block times the velocity squared. And on the right-hand side, we'll have the potential energy, the final potential energy, that's equal to the mass of the block times the magnitude of gravity times the height, h. Plus, this energy loss due to friction, that's going to be calculated as the force of friction, let's call that little f, times the displacement of the block. So this is going to be the equation that we're going to use to solve for d, the displacement, or in other words, the distance that the block moves up the incline. Now, one thing that we currently don't know is, what is this force of friction right here? So let's write that down here. The force of friction is simply equal to the normal force acting on the block times the coefficient of friction. So we know the coefficient of friction, we're told that's 0.3, but what is the normal force on the block? So to figure that out, here's what we need to recognize. There's going to be a force of gravity working on the block, and that force of gravity is going to be directly down. And the force of gravity is calculated as the mass of the box times the magnitude of gravity, g. Now, because we're working on an incline in this example, we can actually break up this force of gravity into its components. So we can say there's a perpendicular component, so the component that is directly perpendicular to the inclined plane, and there's also going to be a parallel component, so the component that's parallel to the inclined plane. Now, the magnitude of this component that is perpendicular to the inclined plane, that's simply going to be the force of gravity times the cosine of this angle right here. So we'll say mg times the cosine of 30 degrees. And the parallel component, that's just going to be mg times the sine of 30 degrees. Now, there's also going to be a normal force that's acting on this box, and it's going to be in the exact opposite direction of this perpendicular force that's pushing down on the incline. So the normal force, let's call that N, will be headed in this direction, and it will have the exact same magnitude as this perpendicular force. So it will also be equal to mg times the cosine of 30 degrees. Let's squeeze that in here. So the force of friction, remember down here we're calculating that, the normal force is mg times the cosine of 30 degrees, and then we have to multiply that by the coefficient of friction, which is 0.3. So here's what we can write in our equation right here. We can say 1/2 mv squared is equal to m times g times h, plus the force of friction we just found is mg times the cosine of 30 degrees times mu. And then we multiply that by the displacement, d, which is ultimately what we want to find. So we need to solve this equation for d. So notice that all of the terms have an m in them, so we can cancel out all of the m's. That actually won't come into play at all. Now, one other value that we don't know is this h right here. And this h, that's the height of the incline. So let's call that h. Now remember, we're interested in finding d. Let's draw that. D is the displacement of the box up the incline. So how far up the incline does it go? So to find d, here's what we can do. We can use a little trigonometry, where if you recall the acronym SOHCAHTOA from trigonometry, this tells us that the sine of an angle in a right triangle is equal to the opposite side of the right triangle divided by the hypotenuse. So what we can say is that the sine of 30 degrees must be equal to the opposite side, which would be this side right here, divided by the hypotenuse. And the hypotenuse would be d. So what we can say is that the sine of 30 degrees must be equal to h over d. So now what we can do is we can solve for h. And we can say h is equal to, if we multiply both sides by d, we get d times the sine of 30 degrees. So we can replace this h right here in the formula with the d times the sine of 30 degrees. So when we do that, here's what we get. 1/2 times velocity squared is equal to g times d times the sine of 30 degrees plus g times the cosine of 30 degrees times mu, the coefficient of friction, times d. So now to solve for d, notice we can factor out a d on this right-hand side. So we get 1/2 v squared is equal to d times g times the sine of 30 degrees plus g times the cosine of 30 degrees. And lastly, to solve for d, we can divide both sides by this quantity right here. So I'm going to go ahead and rewrite that up here since we're running out of room. Okay, so here's the equation that we left off on. And remember, we said to solve for d, we just need to divide both sides by this quantity. So what we end up with is d is equal to, we have 1/2 v squared divided by this entire quantity right here. So we have g times the sine of 30 degrees plus g times the cosine of 30 degrees times mu, the coefficient of friction. So now what we can do is just fill in all of these values and we'll be able to solve for d, the distance that the box goes up the incline. So here's what we get. So when you punch all of these values into a calculator, it comes out to d is equal to 32.5. And we're talking about the distance up the incline, so we'll say meters as our units. So that will be our final answer. That is how far up the incline the box will slide before it comes to a stop.